Okay, so all this integral stuff is just exactly what we have on the left-hand board here. And all I'm going to do is put in explicitly what this is here in the exponential. So I over h bar sum over j's from 0 to n minus 1, delta t qj dot, so we get q j plus 1 minus q j squared over delta t. Okay, so remember the derivative in here is just defined as the difference between the q and the next q over delta t. And so we get that squared over delta t squared, and one of the delta t's cancels with what's already in that exponential. So the point is here, in the sum, okay, we sum over all these things, but everything in here is at most quadratic in any of these q's. And so we can do integrals then of exponential of something quadratic. So this is just Gaussian integration, and so we can actually evaluate this thing. So it's a bit messy, so what I'll do is I'll just sketch the important steps that you have to do, and I can leave this partly as an exercise for you. So the reason it's slightly non-trivial is, of course, each value, so say q1, will appear when I put j equals 0, because q1 appears here. But of course, it also appears in the factor when j is equal to 1. So it's not just a simple sum of these squares. So they mix up. So it's messy to just expand it all. But what there is there's a nice way to work up doing an integral one at a time. And when you integrate the Gaussian, you end up with, again, something that's quadratic and exponential quadratic in the other variables. And it works in a nice way. So you can, the one, basically for an arbitrary qj, oh, sorry, there's a factor of m in here because, of course, it's m over 2, in fact, because it's a half m q dot squared is the kinetic term. So sorry, I missed out that factor. Right, so what we get then, well, the constants are, so we've got I m over 2 h bar delta t. These are just some overall constants. So the term that can involve qj plus 1 minus qj squared. And what you would imagine, of course, we've got the term for the j1 lower down, so qj minus qj minus 1. But actually, what we'll see is it's useful to stick in some factor of alpha. So alpha is just some constant here. And do this integral. So obviously, alpha equals 1. This is what you would do for j equals 1, because it would be q2 minus q1 all squared plus, and then you'd have q1 minus q0, when q0 and qi, initial position, are the same thing, with alpha equals 1. So what you find is when you do that integral, you get a form back that's like, in that case, q2 minus the initial position all squared, but with an overall factor in front of it. So we allow some arbitrary factor. So you just keep doing the integrals in step like that. So this just Gaussian has just got two terms. So now you do just expand these brackets, collect the terms, and use the formula, which you either know or are on the handout. And the result you should get is square root of 2I pi h bar delta t for m times 1 plus alpha, and then some exponential which is the same sort of form. So the factor is alpha over 1 plus alpha, and then you end up with qj j plus 1 minus the initial position squared. So you see, you do the integral, basically what's happened, you've got some factor out in front of it. You've got rid of the qj, of course, because you've integrated over it. And what you've got left is something that's of exactly the same form as the type of things you have up there. It's now qj plus 1 minus qi squared up to some different overall factor. So you start off, when you do the first integral, as factors 1. The next integral, the factor is then 1 over 1 plus 1, so it's a half, and so on. Okay, so that's the main integration you need to do. And so what you find then is when we include one of these factors, the square root of one of these factors, it essentially cancels off most of what appears in here. So if you want to think about it a little bit, you start off, first term alpha will be 1, the next term you get 1 over 1 plus 2, which is a half. And then when you put a half in here, you'll find that the next time you're getting a third, and then you get a quarter and a fifth. So the general term you get, alpha will be 1 over j, whichever j you've chosen to do your integration over. So So it's 1 over j is the thing that goes in there. And you'll find that when you cancel off this bit, which is one of these square roots there, then all you're left with the term then with that value of alpha is j over. So it's, j over j plus 1, if that's not very readable. And exponential of im over 2h bar delta t, 1 over j plus 1, qj plus 1 minus qi squared. So this is, of course, precisely, the point is this is just exactly of the same form. We've gone from integral, this time it was qj with a 1 over j in front of it, and now the term we get now is a qj plus 1 minus qi squared with a 1 over j plus 1 in front of it. So you can just keep doing these integrations. Putting it all together, then you should find the result for this q e to the minus I over h bar. So this is the path integral we wanted to find. So the point is you've got n minus 1 of these integrals, and so each one, as we've seen here, absorbs one of these factors into it. So one of these, so n of these square root factors here. So when we do n minus 1 integrals, we absorb them all apart from one factor. So there's one of these factors left over. Okay, so that's that square root factor. And then you see as we multiply all these factors together, then of course the denominator of one term cancels the numerator of the next term. So I multiply that, but the next one would be j plus 1 over j plus 2, and so on. So it started from j plus 1. So eventually all that simplifies to is square root of 1 over n, the final value I reach with j. And likewise in here, the last integral I do is with j equals n minus 1, because that's the last one I have here. And so I end up with qn, which is the same as my final value of q by this property here, my endpoint. And so I'm left with one of these exponential factors. So it's an exponential of im over 2 h bar delta t, and that thing is n, so I multiply it by n. And then I get q, or q final, whichever notation I use, minus qi squared. And basically we're done now. It's trivial to take the limit n goes to infinity because n only appears here, and, well, I can put these two square roots together here. So n only appears multiplying delta t. So n times delta t is just capital T. So we get n intervals of size delta t to make up the full interval. So these just go together to give capital T. That just goes together there. Sorry, I'm calling it little t in this example. It's the thing that appears up in there. And that goes together to give us the time t. And we'll see that's exactly the same as the wave function we start with. So there's no n dependence at all in there, so you remove the limit n goes to infinity because it doesn't depend on n. Yeah? Sorry? The first, which line, sorry? Ah, thank you. Yes, right, good. Okay, so that's us finished then. That's the example then for the free particle. So what you can do is you can also do the same sort of thing for the harmonic oscillator. It's slightly more tricky, but again, you can do it because it's just a quadratic Lagrangian. Another thing you can obviously check, so it's a good, I should just say, you can check that this thing so this should be, if you put in the classical path, then you evaluate the action. So again, this is just a few lines. Then you should find that that's exactly what you get, what appears in here, well up to the I over h bar. So that's a check of what we said before, that you got this thing here is just a function of, again, I've changed my notation, so it's little t. So it's a function of the time, and this part here is the exponential of y over h bar times the classical action. Okay, so as I said before, this path integrals, there's a few steps I missed out there, so you'll notice that it's quite a long method compared to some of the other methods, in particular the one I left you with where you inserted this complete set of states, of momentum eigenstates, you'll find is just a very quick calculation. So it doesn't appear to give us anything particularly useful as far as calculations in quantum mechanics are concerned. But what it does give us, of course, is a different interpretation. It's the idea of why the particle starts at some initial position and then after some time you've got a chance of finding it spreading out, is essentially because it's allowed to take all sorts of possible paths. So it's like the particle is just wandering about in space. So that's one idea of why the particle doesn't stay fixed where it is, because there's some chance that you can find it, because if you set some final position for it, then of course there are lots of paths that go to that position. But basically in quantum mechanics it's just a different way of doing things, and it's not usually actually the most convenient way. But what you'll see in field theory is that you extend this. So obviously simple extension is we do one-dimensional system here. I could